So, if I was going to summarize section 4.1a, our last lesson, in just a few kind of thoughts, bias is bad. Bias occurs when you're consistently over or underestimating something. It has to be favoring one side. And the only way to truly eliminate bias from your data collection process is to have a random sampling technique. Randomness eliminates bias. People cannot be random in of themselves. You have to use some sort of a strategy to collect that random data. And in this section and the next one as well, 4.1c, we're going to talk about different methods you can use to get a good random sample. So the basic model for a random sample is appropriately called a simple random sample, abbreviated SRS. A simple random sample, by the way it's named, is going to be the most basic version. If I asked you guys to tell me how you would collect data randomly, there's a very strong chance what you would describe would be some sort of SRS. Now, the book definition of a simple random sample is a little bit weird looking, and it's written on there so you guys can see it. But let me explain that real fast. It is a little nitpicky of a definition, but it's something that is important for reasons we'll talk about later. So a simple random sample means that every group has the same chance of being chosen. So if I'm looking at everybody in Missouri, and I want to get my little sample of 500 people that I'm going to use, this group of 500 people is just as likely as this group of 500 is just as likely as this group, etc. Every group has an equal chance of being selected as the group. So every group of n individuals. The variable n, by the way, is a really important variable in statistics. Lowercase n is the variable that we will use all year long to represent our sample size. So make sure you make note of that as you're writing out your definition right here. Little n stands for the sample size, and every group has the same chance of being chosen. The definition is a little weird, but actually thinking about what an SRS is isn't so bad. There are lots of ways you can design one. You can do what's called like names in a hat, where like if I wanted to look at our school and I wanted to pick 50 kids for a survey, I could put everybody's name on a piece of paper that's the same size, put it in like a big box and shake it up, and then pull out however many people I want for my survey. That is an example of an SRS. I could, instead of putting everybody's name on a paper, get a list of everybody's name and number everybody off 1, 2, 3, 4, 5, etc., and randomly pick my numbers using some sort of technique. When you pick your unique numbers, there are two main ways of doing so that we'll talk about. One option for getting your numbers is with technology. So we've done that already in a few of our activities where I've had you do randint on the calculator, or you can use a website that generates random numbers. That would be fine. You can also do random numbers using a table of random numbers. Now, what does that look like? A table of random numbers. Basically what it is, I've got an example in our slides that came out of your book. I don't think I included this in your version, but this is in your textbook on page T5 at the very back. It's just a table of random digits that somebody already like compiled for you. So these numbers were generated randomly, and you can use this to collect your data instead. So let's look at how an SRS works on this example right here. So I am at a mall, and the mall has 21 stores in it. And I want to choose 3 of those stores as my sample to figure out how late they want to stay open during the holiday season. So I could sit there and I could write down each store's name on an index card, shake it up, and just pick my 3 stores that way. That wouldn't be very hard for a problem like this. That might even be a good way of going about it. But this problem is asking us to instead use table D, which is our table of random numbers here. Okay? Now, before I get to that and show you how that works, if I were to do this with just a calculator or something like that, I would number off all my stores 1, 2, 3, 4, etc. And you would do the same sort of thing right here. So you would have to put a number on each store. Don't write this down yet, though. So I would call these stores 1, 2, 3, and so on, 4, 5, 6, 7, 8, 9, 10, 11, and so on and so on. The trouble is, what's going to end up happening is when I go to this table, I'm going to pick digits out of this, and these are going to represent the stores that I talk to. If you look at these first 2 numbers right here, though, it's 19. Does that mean choose number 19? Or does that mean choose number 1 and then number 9? When your digits are different sizes, like you have 1-digit numbers, 2-digit numbers, and so on, you have to make sure they're all the same size or you're not being fair in how you set things up. So this actually would not be okay if I was using the table. For a calculator, I can just type in 1 to 21 and the calculator knows what's going on. But when you use a table, all the digits need to be the same size. So for a table, actually, let me go ahead. Keep doing that. I'm going to erase what I've got on here because I'm going to do one more change as well. So let me erase that, and I'm going to write a little note up top. So for a table, all digits are the same size. So for a table, all labels must be the same size. So I can't just go 1, 2, 3, 4 up to 21. I would have to go like 0, 1, 0, 2, 0, 3, 0, 4, and so on like that. That way they'll all be 2-digit labels. Another thing with this that I'm going to talk about, if I'm using a calculator, I can just say, hey, calculator, go from 1 to 21, and we're good. When you use a table, you also need to specify numbers that you don't want to use because the table doesn't know if you want numbers like 54 and 87. So you have to talk about what numbers are not allowed as well. So you also need to talk about rejected numbers when you do these. So I want to reject everything past the 21st number. What'll happen is people will go 0, 1 to 21 in this problem, and they'll talk about, oh yeah, everything over 22 you get rid of. But if you do it that way, you're forgetting about the number 00 or the number 0. So basically, long story short, when you're doing a table problem, I find it best to start at 0, 0 instead of starting at 0, 1. Start at the very smallest number that could be on the list. You could still start at 0, 1 and then reject 0, 0, but I'm going to go 0, 0, 0, 1, and then I'm going to go all the way up to 21. I guess it won't be 21 anymore. If you start at 0, 0, you're going to go to 1 less. So I would be going all the way up to 20 when I do this. So you guys get the idea when I do this, but that will be number 20 all the way over here. So I'm going to go to my table right now, and I'm going to show you guys how this process would work for selecting your stores. Okay, so I'm going to erase this for a second so it's not crowding my vision. All right. So on my table, you start at the beginning or whatever row you randomly decide to use. I'm just going to start at the top. And since my labels are 2 digits long, I have to take the digits 2 at a time. This is just a line number. You ignore that. My first real number is a 19. 19 is a store on my list because my list went from 0, 0 to 20. So I'm going to keep 19. That's a store I want to talk to. My next number is a 22. Oh, I didn't have a 22 on my list. That gets rejected. And then there's one number left over right here. You join that up with the next number. It's done in chunks of 5, so you don't lose your places easy. 39, not on the list, cross it out. 50, not on the list, cross it out. 34, no. 05, that's on my list. So that's going to be in my sample. And then I just keep going until I get my third store. 75, no. 62, no. 87, no. And then 13 would be a yes. It didn't happen on this problem, but let's say, for example, this said 19 instead of 13. You wouldn't want to go to the same store twice, so you would also reject repeats. That's something we'll talk about, is just making sure that you don't count repeats when you do these problems. But I got my first 3 unique numbers right here. Those are the stores I would talk to. So let me backtrack now. And if I go to my last slide, try to go to my last slide, 19, 5, and 13 are my stores of interest. So you guys should still have your labels right there. Mine went away. But if this guy way down here at the end was a 20, then I guess this would be number 19. So I'd want to talk dividing world. 0, 0, 0, 1, 2, 3, 4, 0, 5 would put me right here. And then 13, so 6, 7, 8, 9, 10, 11, 12, 13. So it looks like my stores that I randomly selected would be the destination tan, the Nike factory store, and Vitamin World. And I would talk to them. So using a table, not terribly fun. It's a lot better just to use technology. Like tables are frankly kind of annoying, but you do see them periodically on the AP test. If I give you a problem and I say, hey, use your calculator, I, as your grader, have no way of knowing if you actually did it or like checking your work or anything like that. But if I give you like a little strip of a number table, I can make sure that you get what you're supposed to get. So I can follow your work. So it's not something you would do in real life if you were collecting data. You'd use technology because it's easier and makes more sense. But the table is important for the purposes of testing. So make sure you're familiar with how those operates. So yeah, that was an example of an SRS on our problem, simple random sample. And let's go ahead and talk a little bit about a few things with regards to this activity. We talked as I was going through this, I mentioned replacement right here. If something is with replacement, you can pick the same number more than once. In my problem, picking the number 19 twice wouldn't make sense. Most times when you're doing a survey or something like that, you would never pick the same person twice. So we actually, when doing surveys, use without replacements a lot more often. So without replacement is going to be more common for surveys. So without replacement means you don't put the number back. And how should you account for this difference when using a table of random digits or whatever? Later on, I'll show you guys how to write up one of these because I just talked through it here. But on a test, I might ask you to design me a random sample, and you'll have to like give me boom, boom, boom steps for this. You have to make sure you mention whether or not repeats are allowed. So when you do problems of this nature, always make sure you address what happens to repeats. All right, so let's keep things moving here. In our next slide, it references the activity that we did. We did like a little demonstration with this corn thing in class. So we've talked now about a simple random sample, SRS. We've done an example of it with our mall stores. It's not that bad to understand an SRS. This activity with the river develops, though, a more sophisticated technique for collecting data. That's not just a simple random sample. So I talked about in class how I want to have a farm. My dream is to own a farm when I get older, and I'm going to grow corn, and it's going to be so amazing. And I purchased a plot of land near the River des Peres. So I got myself a sweet package of property right here. And I want to see how much corn is going to grow on my land. And it's broken up into 16 little parcels. What I had you guys do was break up this parcel of land 4 or 3 different ways and pick samples of size 4. So n was 4 for all of these. This first graph, I just did a simple random sample where every piece of land was numbered from 1 to 16, and I just picked my 4. If I did it that way, I could have it where my numbers end up being boom, 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 like that. It could be here, 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 here. It could have been all over the place when you were doing this. But it's a simple random sample. It's good. It would not be biased, and life is fine. So in this problem, that was our first one, and I'll talk about results on that in a second. The second problem, I had you do what's called a stratified sample. Stratified samples, you break the population up into separate groups and you sample some from every single group. So this problem, I had you break it up and I stratified based on how far you are to the river. When you do a stratified sample, you have to have a variable that you think matters in some way. Distance to the river is something that would make a big difference in how much corn I'm going to be able to grow. I mentioned living on the River des Peres, so maybe being close to the river is actually a bad thing. Or if you have a nice river, then it's going to be good to be close to the river. Now, if you stratify this way for the corn problem, you pick one number out of each row. It is entirely possible that you pick all 4s. Or all 1s, or you could get a good mixture right here. But if you stratify this way, it's actually not such a good thing because you could get a lot of stuff that's really close to the river and that land could be different in some fashion. So we did the problem one more time, but this time when we stratified, we went the other direction. So this time I had you stratify by column. So when you do it this way, what you're doing is you are ensuring that you get one piece of land at each distance from the river. You're going to get one of these. You're going to get one of these, and one of these. So let's say my sample was like boom, 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 like that. That's good because I got something close, something medium close, something medium far, something really far away. And this should give the best results overall. So as a class right here, what we did after we collected our data is we looked at what everybody's average was. So this box right here is like the big reveal. It's how much corn was on each plot of land. And as we talked about, the river was like over on the side, and land close to the river grows lots of corn. Land far away, not very good. The average, if you average all 16 of these, was 70 for all of these. So with the simple random sample, what we usually see is we see a lot of spread to this data right here. So maybe my data looks, I don't know, like this. That is not biased. Remember, bias means you're favoring one side. And if you collected your data randomly, it's not like all of us ended up too high when we did this, or all of us ended up too low. We just have more spread to our data. Fancy word for spread is called variability. So I'm going to write that down right here. It's a vocab word we will talk about a lot in this class. This graph right here ends up being fairly high variability. So your answer and my answer could be pretty different based on which pieces of land we chose randomly. Then we stratified by row. And when you stratify by row, that I said was not a helpful thing because you still could very much get pieces that are all close to the river or something. So usually from year to year when I do this, it's actually even a little bit worse than the original when you stratify by row. So if you stratify by a bad variable or you do a bad job, you can actually make things worse. Some years it's not worse and it's just about the same, but neither of these graphs is super desirable. If I look at one of these pictures, I kind of don't know what to think. My corn yield could be as low as 10, could be as high as 130. I'm just all over the place. But if you stratify by column in this problem, what ends up happening when we graph our class data is everything is a lot more compact. Instead of being all over the place, we usually see this kind of a picture right here. This is low variability between estimates. So low variability between estimates. And low variability is something we like. We like low variability because then we have a pretty good idea of what's actually happening in this problem. It won't let me draw my smiley face. Oh, this is so sad. There it is. All right. So low variability is a good thing because then we have a good idea of what's happening. Just because something has low variability doesn't automatically mean it can't be biased. Let's say this, like, I don't know, the soil measuring thing I did ended up being where it wasn't working right and everybody's was too low. Then you could still be biased. But low variability, assuming that we're not biased, is a good thing because it clusters around what the answer is supposed to be. Kind of wouldn't know what to think up here. I'd have a pretty good idea about what my average is going to be right here. So that was the thing that the activity was getting across. And I'm talking about this a little more right here, and you guys can write these down. Stratified sampling. You're going to choose a variable that you think matters. You're going to break the population into groups based on that variable, okay? So everybody within this group or within this group, all the people inside of a group are similar to each other. Classic example that I like using in class. Let's say I wanted to know at our school what kids' opinion is on freshmen being allowed to attend prom. Should freshmen be able to attend prom? If I think about that, I could just do an SRS and get some of everybody, and that would be cool. But maybe I would get more seniors in one sample, more freshmen in the others. My results, if I do different samples, are going to be fairly spread out. They're going to have high variability. But if I break you up and think, well, year in school probably makes a big difference. Freshmen are probably like, yeah, let's go to prom. Seniors are probably like, oh gosh, no, I don't want them there. So the year you are in school makes a difference. What I would do in that situation then, instead of just numbering off everybody at MRH and using that as my sample, like doing one big list, I would break you up into bubbles. And this could be like the freshman bubble. This would be like the sophomore bubble, the juniors, and the senior bubble. And I would pick a separate SRS for the freshmen. So I would make sure I get 20 freshmen for my sample. Then I would go and I would get 20 sophomores, 20 juniors, 20 seniors. So you break it up into a variable that matters. And then once you do that, you pick some out of each group. That probably makes sense now, but in the next section, I introduce cluster sampling, and people mix those two things up all the time. So just make sure you're able to keep these straight. We'll talk more about it in the next section. Why do we stratify sample? Talked about it already, but you do it when you think you have a variable that will make a difference in your results. And when you do this, why should you do this? It makes your results more consistent, which makes it easier to tell what's going to happen. So it decreases variability between samples, which is good because then you know what to actually think.